All right. Audric, if you were planning to join us today, my apologies. I'm assuming that you're in the middle of your visit. So I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just help us to glorify you what we do and understand a little bit more about eigenvectors and eigenvalues. Lord, in your name I pray, Lord Jesus. Amen. Okay, so we get straight into it. Here we go. Whoop. So we're in section 4.9. And as always, we're in Introduction to Hilbert Spaces with Applications by Lokneth, Debneth, and Piotr Makuzinski, which I'm probably mispronouncing. But so eigenvalue and eigenvectors. So here we go, definition. Let A be an operator on a complex vector space E. All right, a complex number lambda is called an eigenvalue of A if there exists U not equal to 0 for which AU equals to lambda U. And every vector satisfying that equation is called an eigenvector of A corresponding to eigenvalue U. Oh, that's not quite the standard definition. That's not quite the standard. I see what he did here. I thought he had a mistake later in the section, but apparently not. And I say it's not quite the standard definition because he's a very sneaky person. He's just included 0 as the eigenvector. If he says the set of eigenvectors is the set of vectors that contain this, so you might say eig lambda is equal to U in E such that AU equals to lambda U. So if you said that was the lambda eigenspace, you'd be including 0. So usually in undergraduate linear algebra, and this is the kind of annoying thing, I'm careful to say that the eigenspace is only eigenvectors with one exception, 0. But he has crafted his definition in a very sneaky way as to say 0 is an eigenvector, which is to avoid this discussion, which we're now having. But anyway. Let's see here. Example 4.92. Yeah. Let S be a linear subspace of inner product space E, and let PS be the projection on S. The only eigenvalues are 0 and 1. All right. So example 1 is from a section we skipped, but that's just the reason to cover it, actually. So if you have S is a subspace of the complex eigenvectors. Well, no, wait a minute. Inner product space E. Then a projection, you can talk about the projection onto the S subspace, a mapping from E to S, right? Or, well, you could, I guess, this is where I'm going to get into trouble. I don't know if he's defined this to go from E to E or from E to S. Let's say it goes from E to E, just for the sake of discussion. Then it's an operator, right? And the properties, but the range of it, right, is well, it's equal to S actually. It's onto S. So this is the projection onto S. If you have, basically the way it works is if you have Z is equal to, say, X plus S, where, you know, X is an element of the perp of S, and S is an element of S, right? And if you're in an inner product space, you can define the orthogonal complement of a subspace, you know. And in this context, then PS of Z is equal to what? It's just equal to S, right? It kills the S part and leaves you S. So in particular, if X is, well, now I'm using X, listen to me. If, well, let's just say X is not, Y, there. If Y is an element of S, right? Actually, let me make U. My bad. If U is an element of S, then what does the projection of S acting on U give you? Just U again, right? Which of course is 1 times U, right? So certainly the projection operator has eigenvalue 1, and it's got a lot of them, depending on how big S is, right? So in fact, that means that with regard to this, then you can see that Eig1 for my projection operator would just be equal to S. Well, I should be careful. I don't know for sure that there's not other, I mean, how in principle do I know that there's not any eigenvectors with eigenvalue 1 outside of S? I guess I know that because for the vector outside of S to be in there, it would mean that P of that vector is equal, since the range of the operators inside S, that's pretty much reasonable. How about if U is an element of S perp, though, what do you get? Right, then that means that when you act on the projection operator acting on such a U, you get 0. So in fact, you can see that the eigenspace of eigenvalue 0 would be the perp of S. So, and in fact, this gives you an example of a general theorem about eigenvalues, right? Like if you have some operators are built such that you can pick a basis for your space, right? If he was finite dimensional. If he's finite dimensional, you can see from this that, in fact, S is a diagonalizable operator. Because E, you know, E is equal to S direct sum the perp of S if the dimension of E is equal to N, right? And the dimension of S, let's say, is equal to little m, which is less than N. Then if you have a basis, say V1, V2, Vm, and then Vm plus 1. Well, let's say W1, W bar. I don't want to put bars on it. Just W1, W2, Wn minus m, right? Is basis for E, where I'm assuming that here this is a S basis, and this over here is an S perp basis, right? Then if that's the situation, what does the matrix of the projection operator look like with respect to this basis? If I call this thing beta, right? Then the matrix of the projection, oh good grief, the projection operator with respect to this beta basis, right? what it looks like is, well, the way you do that, right, is you take the projection operator, you let it act on the first thing in the basis, right? You calculate the coordinate vector of that. You let the projection operator act on the second thing in the basis. You do the coordinate of that, and so forth and so on. This is the definition of the matrix of a linear operator with respect to a basis, using the basis beta for the domain and the range. The way to calculate the matrix is you find out what happens to the vectors in the basis, and then you calculate the coordinates of that. So this is literally, you know, the coordinate. What's the coordinate vector of v1? What's the coordinate vector of v2? Right, all the way out to the coordinate vector of vm, and then you've got 0. But if this is the basis, right, what is the coordinate vector of v1 if v1 is the first thing in the basis? Well, it's exactly e1, right? So this is literally e1, e2, all the way out to em, and then zeros. So what the matrix looks like is the m by m identity matrix padded with zeros. And this is an example of, I mean, it's a pretty simple example, but here we have diagonalized. We've diagonalized the projection with respect to this usual basis. The basis here is an example of an eigenbasis, because every basis element here is an eigenvector of the projection operator with either eigenvalue 0 or eigenvalue 1. Now, not every transformation on a finite dimensional space permits an eigenbasis. Right? One of the things that we're after in this section and the next section is understanding when is it possible to diagonalize an operator. So for this one, you can. And more to the point, if you can, it's possible to write the whole space as the direct sum decomposition of eigenspaces. And we'll be able to prove that eigenspaces for distinct eigenvalues are perpendicular subspaces, among other things. Okay, anyway, let me get back on track here. I think I'm spending a little bit too much time. He doesn't say all these things, right? Let's see here. Theorem 4.93. The collection of all eigenvectors corresponding to an eigenvalue is a vector space. So let me erase this example. Once I find my, oh man, did I do that? All right, well, it looks like we're on poor man's eraser today. Well, it's working at the moment, so we're mostly. So theorem Ig lambda subspace of E. I would point out that that's true even when this is true even when lambda is not an eigenvalue. As I've defined it, it's just stupid. See, if lambda is not an eigenvalue, what is the solution of AU equal to lambda U? There's always a solution. What can you make U equal to here and solve this equation?
Oh, because we have 0.
Right, 0 is always there. So you always have 0 as a solution. It's just if 0 is the only solution, then lambda is not an eigenvalue.
Interesting.
If U equals to 0 is the only solution, then lambda is not an eigenvalue. But if you define Ig lambda like this, it's still stupidly true that my theorem holds because the zero subspace is still a subspace. All right, anyway, let me stop saying really stupid things. Definition, eigenspace. Great. The set of all eigenvectors corresponding to an eigenvalue lambda is called the eigenspace of lambda. The dimension of that space is called the multiplicity of lambda. If it's multiplicity 1, it's called simple or non-degenerate. An eigenvalue of multiplicity greater than 1 is called multiple or degenerate. In this case, the dimension of the eigenspace is called the degree of degeneracy. So, definition, the dimension of eig lambda is equal to the multiplicity of lambda. I will say here, I'm not totally in favor of this language. I would prefer to call this the geometric multiplicity. That's what I would call it in undergraduate linear algebra. It's the geometric multiplicity of lambda. And then, so if the dimension of the eigenspace of lambda equals 1, then lambda is simple eigenvalue. Otherwise, it's called degenerate. All right. Ooh, I just broke something in there. Okay, so for example, my example here, if S is one-dimensional, right? If S is one-dimensional, if S is a line, then eigenvalue 1 is a simple eigenvalue, and eigenvalue 0 is probably a degenerate eigenvalue, unless you're in two dimensions, in which case 1 and 0 are both simple. But otherwise, if S is more than one-dimensional, then you have multiple eigenvectors, so your eigenvalue 1 would be degenerate. You may have experienced some of the trouble that comes from that in physics when you have a degenerate eigenvalue. That makes it fun. Let's see here. He has an example 2. I'll call it example 2. He has a u of t equals to integral from 0 to 2 pi of cosine of t minus y u of y dy. So, and I guess he works it out here. So, if this is equal to lambda u of t, right? That would make this an eigenvector with eigenvalue lambda. Man, how does he do this? He says let u. Okay, well there's the eigenvalue equation, right? Which he rewrites as that. Okay, so he pulls. Oh, okay. So this is what? This is cos t, cos y, minus sine t, sine y, right? Yes. And what happens when you integrate that thing? Does anything happen?
With respect to...
Oh, we don't know. It's got that multiplication by u of t, right? So I guess, let's see, what's he do? He just breaks it up. Okay, just breaks it up. So he's like, so what you've got is lambda u of t is equal to cos t, integral from 0 to 2 pi of cosine of y u of y dy minus sine of t, integral from 0 to 2 pi, sine of y, u of y dy. I'm genuinely interested. How does he solve this equation? Then he's like, this means that for lambda not equal to 0, it's a linear combination of cosine and sine functions.
With the weights being the intervals themselves.
Huh. Oh, okay. So this is A, this is B, U, well, lambda U of t is A cos t plus B sine t. But I guess you could just say that, right? Absorb the lambda into the A and the B.
No.
Yeah. And then you can plug that back in up here, right? And what would that give you? Oh, well, I don't know why I'm doing that.
Yeah, you're teasing me.
Oh, okay, well, that is what he does. All right, fine. So we've got A cosine y plus B sine y, is that right?
So this is using like t equals y and plugging that in.
Does he plug it into the, oh, no, he plugs it into the expanded equation. I'm plugging it back into the original one. I should plug it into that one. My bad. You know what I'm saying? I chose the wrong equation. I'm supposed to plug it into this one. And so, all right, just let me sort through it here. So if I plug this into here, the cosine sine term integrates to 0. So you just get the cosine term. You get like cosine t integral from 0 to 2 pi cosine squared y dy plus sine minus sine t. There's an a here, right? A minus b sine t integral from 0 to 2 pi. I don't know. Well, fine. Sine squared y dy. Again, my logic is just this. As you plug in u of y up in there, the sine cosine, it's integrated over a multiple of periods because sine cosine is sine twice, and that goes over 4 periods. Well, 2 periods for 2 pi. So that integrates to 0. And this integrates to, that just integrates to, so cosine, so here's the trick. Cosine squared and sine squared are symmetric over the 0 to 2 pi. If you integrate d theta from 0 to 2 pi, you get 2 pi. Since cosine squared is half of it, it integrates to pi. So this is pi, and that's pi, because it's half of the integral of sine squared plus cosine squared. From 0 to 2 pi. This is a trick. So this gives me a pi cosine t minus b pi sine t. And that's equal to this above, right? So then what you do there is you've got linearly independent functions, yeah? This and that, but sine and cosine are independent, you know? So we can equate coefficients, and when you equate coefficients of cosine, you get yourself lambda A is equal to, wowzers, sorry Audric, A pi and lambda B from the sine terms is equal to minus B pi. So therefore lambda equals to pi, or lambda equals to minus pi. And let me be more clear. If lambda is equal to pi, B is equal to 0. If lambda is equal to minus pi, we have to have A equals to 0. See, because we have to solve both of these at once. Those are simultaneously imposed. So you see we have two different eigenvalues, pi and minus pi. And the pi eigenvectors are a cosine function. The minus pi eigenvectors are the sine functions. Well, sine function, right? Well, okay, any scalar multiple of that. As usual, you know, you got one eigenvector, you got infinitely many, since we're working over a field of characteristic 0. If you ask me, well, how do eigenvectors work over a field of finite characteristic, I would say, go find another professor. It's not my thing. My life is finite here on Earth. I mean, we may or may not get to do math in heaven. I don't know. I mean, I hope so. Maybe you won't care. I don't know. I mean, heaven's supposed to be full of things that are beautiful and valuable. And I'd like to think math is part of that. Anyway, let's see here. So let's see here. Note that if lambda is not an eigenvalue of A, the operator A minus lambda I is invertible, and conversely. All right. Remark. A minus lambda times the identity, which I'm going to write like this. He keeps writing it with his funny scripty eye, but I'm going to use this for the identity operator, if that's okay. This is invertible if and only if lambda not an eigenvalue. And the reason for that, among other things, is to say that's invertible, right? So if A minus lambda I inverse exists, well, we don't know about determinant in infinite dimensions, but notice that if we have AU equals to lambda U, then that means that A minus I times A minus lambda I times U is equal to 0. Yeah. But then, if this exists, then we can hit that by the inverse operator. And the inverse operator of a linear operator, even in infinite dimensions, it's still linear. So a linear operator hits 0 at 0. And of course, this gives me IU. So U equals to 0. So therefore, lambda not eigenvalue. Because we just proved that the eigenvector equation has only the 0 solution. And this argument's reversible. I mean, like, if you have more than the 0 solution, if you have more than the 0 solution to this, then that means that this operator is not injective. So an operator which is not injective can't be invertible. That would be tantamount to the inverse being multiply valued. This we cannot have. But, okay, so anyway, moving on here. But you're right, it's infinite dimensional, so what's the deal with that? And that's where it starts to get interesting because, well, we can't use determinant, right? I mean, not usually anyway. Maybe, I want to hold out hope that there's a way to define the determinant in a separable Hilbert space, right? For an infinite matrix, like maybe there's something there. I don't know. I'm just speculating, all right? But outside that context, I have little hope for infinite dimensional determinant. But anyway, this is called the resolvent. Resolvent and spectrum. And he says let A be an operator on a normed vector space E. Normed linear space E. Then A sub lambda equal to A minus lambda I inverse is called the resolvent of A. The values for which A lambda is defined on the whole space E and is bounded all right, are called regular values of A. Regular values of A. And the set of all regular values is called the resolvent set, and it's denoted by rho of A. All such lambda give you the set rho of, not rho of lambda, that's to be self-referential, rho of A. Okay, so lambda is an element of rho of A if it's a, so obviously if it's a regular value of A, it's not an eigenvalue. The complement of rho of A in C is called the spectrum of A and is denoted sigma A. So the spectrum of A is equal to sigma of A, which is equal to C minus the resolvent set of A. The spectral radius of A is equal to the supremum of the modulus of lambda such that lambda is in the spectrum of A. In other words, the spectral radius is essentially the least upper bound of the moduli of eigenvalues for A. Oh. Let's see here, what does he say? He says, every eigenvalue belongs to the spectrum, but the following example shows that the spectrum may contain points that are not eigenvalues. And in fact, a non-empty spectrum may contain no eigenvalues at all. Ooh, funky. So it's not as simple as the spectrum of A just contains eigenvalues. It is true that every eigenvalue is contained in there, but that's not to say that they're all eigenvalues. So it's kind of fussy, isn't it? So let's see if we can understand his example. That'll be my example 3. The space of continuous functions on the closed interval A to B, right? And let u be a particular element in there, and define A acting on x at time t will be equal to, oh, just multiplication u of t, x of t. So you say pick a function in there and just multiply by that function, okay? And then we can ask the question, what is the, can we calculate the inverse of a minus lambda I for this function? He just rattles off a formula for it, which means we can derive it with like a second, just take a minute to derive it. Let's do it. So we're asking, let's see here, you've got a minus lambda I, right? Times x at time t, right? That's going to be a x of t, right? Which would be u of t, x of t. I'm getting really tired of writing this t dependence. But then minus lambda x of t, right? All right. And if we multiply this by, so what's the, let's see here. If you want to find the formula for the, yeah, if you don't mind, I'm going to drop some of the notation here. So I've got a minus lambda I times x is equal to, excuse me, ux minus lambda x, right? And so this is equal to y. So if I want to find the inverse, I solve for x. So I've got u minus lambda times x is equal to y. So that makes x is equal to, y over u minus lambda. In other words, the formula for a minus lambda I acting on y inverse at time t should be y of t divided by u of t minus lambda. And that's the formula he has. Okay? So that's how to derive that. That's just like a generic point of order. If you're looking for the inverse of a formula, write down the formula, give a label to the thing you're mapping to, and then solve for the input. That's how to find the formula for the inverse. So there it is. Now what does he say about it? The spectrum of A consists of all lambdas such that lambda minus, okay, so when does this fail? It fails if there exists T in AB, right? Such that what? Such that U of T minus lambda is equal to, yeah. That means that the spectrum of A is exactly the range of U. Right, U of T equal to lambda. He says if U of T equals to a constant function, then lambda equals to C is an eigenvalue of A. On the other hand, if U is a strictly increasing function, then A has no eigenvalues. Notice that this is the set of continuous functions on the real interval. So this is actually, f that go from AB to AB again. So it's a real valued. Okay? let's see here. So the resolvent of A, what was it? It was equal to the the values for which A lambda is defined, right? So this would be the real numbers. Well, excuse me, it would be the complex numbers, right? Because this is complex, you know. So if I follow the definition, it should be the complex numbers. Take away what? Take away the range of U. I guess this begs the question: are you supposed to replace this with the real numbers in the real context? I don't know. I mean, he doesn't say so. Does he imply that with this example? He says if U is a strictly increasing function, then A has no eigenvalues, and the spectrum of A in such a case is the interval.
I guess that would make that sense for U to be increasing if U maps to C.
Yeah, I think he's adopting the convention that we replace C with R in the case of a real operator. It sure looks like that. So apparently we do that, because otherwise the rest of his example doesn't quite make sense. Okay, so in the context that if U is a constant function, then rho of A is just R minus the constant value, right? And then sigma of A is just equal to that constant. And in the case that U is a constant, this literally becomes AX equals to CX. So of course, the eigenvalue is C, and everything is an eigenvector except for the zero function. Excuse me, and the zero zero function is not an eigenfunction. However, it is in the zero eigenspace. Ugh. In the case that the function's a constant, then the resolvent set is everything except for the constant, and the spectrum is the singleton. If the U is increasing, strictly increasing, right? Then that means that U of AB is, equal to U of A, U of B. I mean, that's the range, and so rho of A in this context is R minus that image, the range of U, right? And so in this case, the spectrum is the range of U. And I think in this case, what's he say here? Well, he claims that it has no eigenvalues. So he says in this case, A has no eigenvalues. So why is it that if U is strictly increasing, it can't be an eigenfunction? We just need to think about the definition that's given here. It's going to be something relatively simple. Let's just write it down and think about it, right? So we have AX, right? Is equal to what was it?
Lambda enclosed interval.
Oh, right, right. But that is also, yeah, it's also ux, right? Equal to lambda x. And that has to hold, this has to be on AB, right? I mean, that has to, this has to be a function identity. So, and you know that well, you know that lambda is a fixed element, right?
Oh,
Of in here, so like lambda has to be equal to u of t naught, right? For some t naught.
oh, okay. So you would have to be a constant function, but we're saying it's increasing, so that doesn't make sense.
But that's impossible because u is strictly increasing, so it can't match up for all. Yeah, yeah.
That makes sense.
So yeah, this is okay. So this example serves its purpose. The spectrum of A is indeed non-trivial, right? And yet there is not a single eigenvalue because there does not exist an eigenvector, right? Although you might call it an eigenfunction here to emphasize that the vectors we're talking about are functions. All right, so let's see here. What's up next? Well, the problem of finding eigenvalues and eigenvectors is called the eigenvalue problem. The main source of eigenvalue problems in mechanics is the theory of oscillating systems, right? The state of a given system at a given time may be represented by u of t in h, where h is an appropriate Hilbert space of function. The equation of motion in classical mechanics, acceleration equals to au, where a is an operator in h. Blah, blah, blah. Let's see here. Oh, okay. Yeah. So it's another example that he's giving. Let me write it out. This one's pretty easy. It's nice. So if you're talking about classical mechanics, you might be looking at d squared u dt squared equals to au, right? And so you may or may not have seen this, but if you have a system of springs put together, right? You can write the equation of motion for the system of springs like this, where this is a matrix and these are the coordinates of the springs, right? And so if you had, for example, u of t equal to, sine of omega t times some vector, v, and you differentiate that, twice differentiate that, what do you get? You get, minus omega squared sine omega t times the vector. I'll put vectors on vectors here just to make it more vectory. There we go. And so when would that be a solution? That would be a solution if d squared u is equal to au, right? Which is to say a sine omega t times v. So since this has to hold for all t, you see what you need is you need av equal to minus omega squared v. So, that's an eigenvector of the matrix, but he says, well, so minus omega squared is an eigenvalue of A. All right. Theorem. I will say this. I feel like sometimes the word eigenvalue is used where it's not exactly an eigenvalue in partial differential equations. We'll get to that like one of my future lectures. I mean, I don't know, maybe I just lack imagination. Let's see, if A is a bounded linear operator on a Banach, man, we got everything in here, don't we? We started with a complex vector space, then we're talking about a Hilbert space, now we're talking about Banach space. We just got it all, right? Banach space E, and the norm of the operator is equal to, excuse me, is less than the absolute value of a complex value lambda, then the resolvent, A sub lambda, is a bounded operator. Right. Yeah, because the Banach space is a complete norm linear space, so we define the operator norm on that by the supremum on the ball, right? Oh, there's more. I thought that was it, but here's the punchline. A lambda, oops. A lambda is equal to, check this out, minus the sum n equals 0 to infinity, what the what? A to the power n over lambda to the n plus 1. Cool. And the norm of the resolvent, son of a gun. The norm of A sub lambda is less than or equal to 1 over the modulus of lambda minus the norm of A. To which I say, what? This is not something I have taught before, as far as I remember. Huh. Curious. The proof does not look that intimidating. It's only about a half a page. So we can try it. Famous.
How else were we missing like a geometric series of matrices or something?
You know what? All right, I like what you said. Formal nonsense proof. A minus lambda I inverse is equal to 1 over A minus lambda I, all right, is equal to 1 over A inverse times I minus lambda A inverse, right? Is equal to A over I minus lambda A inverse by the geometric series, that is A times the sum, n equals 0 to infinity of, my radius here is equal to, minus lambda A inverse apparently. And so, we've got minus lambda A inverse to the n power. Oh, I did my formal nonsense wrong. Let's try this again. So yeah, let's factor out a lambda. 1 over lambda minus lambda, actually. 1 over minus lambda times I minus 1 over lambda times A. That's better. At least I'm not assuming A is invertible now. I mean, I want to do some formal nonsense, but I don't want my nonsense to be too nonsensical. This is better formal nonsense. Now I go geometric on this thing. Minus 1 over lambda sum n equals 0 to infinity of 1 over lambda times A to the power n, which is equal to minus the sum. Yeah, A to the n over lambda to the n plus 1. Yeah. And when is this going to be true? This step is legit for 1 over lambda A, the norm of that, right? To be less than 1. Which is also known as the norm of A less than the modulus of lambda. So that's the precondition. The precondition is the one that's necessary for this formal nonsense to be reasonable. And that estimate, once you have this equality, then if you probably if you do like the triangle inequality or something in the limit, it pops that out, probably from another geometric series. Yeah, something like this works for supernumbers as well when you're like inverting supernumbers. There's a place where you end up with like, it looks like you'd have, you know, division by a supernumber. That's just like, again, formal nonsense, but it's funny because what that actually means is you can go and do the legwork and prove that the corresponding estimates work, and while some of these steps don't really quite make sense, it does tell you what you want to prove. So, and the proof, so I won't go through the proof actually because it's in the book, but if you look at the proof, what's he do? He starts by proving that the series of a to the n over lambda to the n is bounded above by another series which is less than infinity, because that's a geometric series right there. You see that? That's his series he's majorizing there with. This is a geometric series. Then he uses the completeness to find a bounded linear operator B that equals that. And then I think what he's really doing here is just proving, so all he's doing here in the past the moreover and before the to prove, all he's really doing is he's showing that if you look at this operator and you multiply it by a minus lambda, you get the identity. That's all that argument is. That argument is just showing that, hey, this is the inverse. So the existence of that formula is given by the appeal to the geometric series, and the geometric series existing is based on this condition. Which is exactly, of course, the condition that we needed for our formal nonsense to work. So, yeah. That is so cool. And then the last estimate, like I said, comes from applying the triangle inequality at the level of the series. And then he again does a geometric series as I have forecasted.
Correct. Oh, yes.
Yeah. So anyway, let's go on. Thank you for suggesting that. That was fun.
That's definitely interesting.
Oh, the representation that we just wrote down is usually referred to